Hi everybody, and welcome to this last day of the BBQ conference. My name is Jenny Wu. I am an experimentalist working in ion trapping down the road at NIST Boulder. And it is my honor to be chairing this first session today. First up, we have Harry Levine from the Amazon AWS Center for Quantum Computing, and he's going to be telling us about long-coherence erasure qubits using tunable transmons.
Great. Can you hear me okay? Awesome. All right. Wonderful. Thank you so much to the organizers for the chance to be able to speak here today at this wonderful Byron Bay Boulder quantum workshop. Inspired by previous talks, we could even add a few more Bs. Breakthroughs in building beyond break-even bosonic qubit maybe for the next year. So thanks to the organizers and thanks to all of you for making it to the morning of the final day. Okay, so I'll talk about erasure qubits today, and this will follow from previous talks that we've already heard in this conference about erasure qubits as one strategy towards hardware-efficient quantum error correction. So we'll build on the standard paradigm of quantum error correction, which is the idea that to preserve logical information, you use some error correcting code like a surface code, and you do repeated rounds of syndrome measurements, where your ancilla-qubits will raise flags to indicate that errors have occurred somewhere nearby. And so you end up with a constellation of syndromes that you then need to decode and say, my syndromes raise flags over here. I draw some kind of path between them and indicate, and that's my best guess as what physical errors occurred, and that's what I'll try to correct. So erasure qubits or erasure codes build on this idea. In addition to getting these syndrome flags, we get extra information, which is that the individual physical qubits raise extra flags that say that an error occurred on this qubit. And typically what happens is they'll raise a flag that an error occurred, then you'll reset the qubit, you'll remeasure your syndromes, and now you can seed your decoding by knowing, at least for the most part, which locations had these physical errors. So this is a much easier problem to decode when you get all this extra information. And as a result, those errors are more tolerable in quantum error correction. So whereas the typical threshold for errors for random poly errors might be around like 1%, the threshold for erasure errors is much higher. 4%, or as Jehan talked about earlier in the conference, in some models, it could be even as high as 8% or 17%, I think. And you could also think about that as there being effectively a larger code distance for erasure errors. For a code distance D, you can correct up to D-1 erasures, whereas only D-1/2 generic poly errors. So it's very nice if your qubits are willing to raise this flag indicating that errors have occurred. And for that to really be practical, we need these properties. We need that the most common error for the qubits to experience should be this kind that it knows how to raise the error. So undetectable errors are bad in that they don't benefit from this property. We need most of the errors to be these erasure errors that raise the flag. That's so-called erasure biased noise. And we need to be able to actually interrogate the qubits in real time to find out that these erasures have happened so that we can feed them into our decoder. Most qubits don't have these properties, of course. And so a question is, how do you define your qubit, or how do you encode a qubit in a physical system that can actually take advantage of these ideas? One paradigm for this is to take a physical system that has some kind of known error channel and define your qubit in such a way that the dominant error channels are not bit flips or phase flips, but instead leakage errors that take you out of the computational subspace. And those leakage errors, if you don't detect them in real time, they can be bad for your error correcting code. But the idea here would be we'd like to have these leakage errors in such a way that we can actually detect them by interrogating if the system is in a non-computational state. So there's several examples for how this can be done. We heard earlier about a beautiful idea with neutral atoms, where you have a qubit, and when you do 2 qubit gates, you drive to this highly excited Rydberg state, where a fundamental limit is that the Rydberg state can decay into a lot of different possible states in your Hilbert space. So that's leakage. But if you can actually probe the atom to see that the system decayed into one of these states, then it becomes a detectable erasure error. And so that's a really beautiful idea and recently demonstrated in 2 amazing experiments from Caltech and Princeton. Superconducting circuits, which is what I'll be talking about today. There's another way of encoding qubits in superconducting circuits that allows you to expose these types of leakage errors as erasures. And this is the so-called dual rail qubit encoding, which we heard about yesterday from Rob Scholkopf's talk, where you take 2 superconducting modes and you encode your qubit in having 1 photon in the left mode or 1 photon in the right mode. So that this fundamental limit of superconducting resonators, which is amplitude decay, rather than causing bit flip or phase flip, it causes leakage to the 0, 0 state. So Rob talked about an implementation using two microwave cavities where the photon is in the left cavity or photon in the right cavity. I'll be talking about a transmon-based version of this, where you have photon in the left transmon or photon in the right transmon. In both cases, just to reiterate this one more time, the underlying components have some T1 decay. This is converted now to erasure errors. Additionally, the qubit manifold is the 1001 state. Those levels should be very stable. Any errors that occur within that manifold are bad. Those are the undetectable errors. And those are the errors that we should try to make very, very small compared to the dominant error of leakage to 0, 0. So with that in mind, the cavity approach is quite attractive because not only do cavities have really long T1 times at the millisecond scale, but they have even longer dephasing times. And so you can expect that the 10 and 01 states have their frequency stability determined by essentially how stable are the cavity frequencies, and those are very stable. And so that gives very low dephasing error within that subspace. Transmons don't have that property exactly. They are compact, and there's a huge amount of effort towards figuring out how to scale them up. So it's an attractive building block, but transmons are noisy. Let's see, can you hear me? Great. Transmons are noisy. And so the question, if you want to build a dual rail qubit out of transmons, is can we nonetheless suppress this noise such that we can have good phase stability within the 1001 manifold, and again, just be limited by whatever the underlying amplitude damping is, decay to 0, 0. So this is possible, and it's enabled by a particular construction for the dual rail qubit with transmons, which is based on the idea that you take two transmons, and rather than just using the bare 10 and 01 states, you have two transmons that you park on resonance with each other, and they're coupled together. So now the 10 and 01 state are coupled strongly, so the eigenmodes are symmetric and anti-symmetric combinations of these two states. So these will actually be the logical Z eigenstates, the logical 0 and logical 1 for the transmon-based dual rail qubit. This is now a low frequency qubit. It's megahertz to hundreds of megahertz energy gap, just determined by the choice of this coupling strength G. So that's a lower frequency qubit than a microwave 5 gigahertz qubit, but it has this property that this underlying transmon T1 is a leakage error to 0, 0, which could be detected and then converted to erasure. And it has an additional really critical property, which is that the hybridization of these levels 0, 1, and 1, 0 leads to eigenmodes that are much more stable in terms of the relative energy gap than the underlying transmon frequency stability. This can be thought of as a two-level system, which has some relative noise, but it's spin-locked with a strong drive, for those of you that maybe know that analogy. One really simple way to get a picture for this would be to say, let's suppose these two levels are not quite on resonance. Maybe they have some frequency fluctuations. So they're coupled with strength delta or coupled with strength G, but with some fluctuating small value delta. The eigenmodes essentially are split by an energy gap, which adds these two terms in quadrature. It's the square root of 2G squared plus delta squared. And so as long as delta is small, the contribution to this combined energy gap is actually quadratic in the strength of delta. So you would like G to be much larger than delta, and then you can get much more stable energy gap here than the underlying transmon stability. So that's the core idea how we hope to get past the noisy behavior of transmons. This qubit encoding has been demonstrated before in these really amazing experiments from MIT, showing both universal single qubit control in this manifold and even proof of principle 2-qubit gate experiments. And in this talk, I want to focus on whether we can use this really as a viable erasure qubit. So whether we're able to indeed take advantage of this noise suppression to achieve really good coherence within this excited manifold, such that we're limited not by dephasing within that manifold, but by the erasure errors that take us out of the manifold. And second of all, we'd like to see that these leakage processes to 0, 0 can be detected in real time and how well that's able to work. So I hope to show you that indeed these things do work, and that this can ultimately come together and be a pretty compelling, surprisingly high coherence building block for quantum error correcting codes. So in this talk, I want to first dive a little bit more in detail into how we set up and operate a dual rail qubit based on transmons. Then I want to talk about characterizing qubit coherence within this metastable manifold compared to the rate of erasures. And finally, I'll talk about doing erasure detection during quantum circuits. Okay. So operation of the transmon-based dual rail qubit. We have two transmons. They're both tunable transmons. They have tuning curves roughly as shown here. And the salient feature would be we just need to be able to bring the transmons on resonance with each other. That's where we get noise suppression of this form. So ideally, we park one of them maybe at its maximum frequency where it's most stable, and then we tune the other one down into resonance. So this is where we get our dual rail eigenmodes. So here's what a typical circuit would look like at the single dual rail qubit level. We start off, the dual rail qubit initializes into the 0-0 state just due to relaxation. So then we start off with a microwave pulse that resonantly takes us from 0-0 into one of these two logical states. Typically, we'll initialize the logical 1. We then do single qubit gates, and the single qubit gates are realized by modulating the frequency of one of the two transmons. So we have two levels, the 1-0 and 0-1 level, they're coupled. If you modulate one of the levels at the frequency of this energy gap, then you drive resonant transitions between these two logical states. And so that gives us a universal single qubit gate set. We can implement, for example, pi/2 rotations by calibrating a pulse length and amplitude. And we can implement arbitrary z rotations just by changing the phase of this flux modulation curve. So that's universal single qubit gates. At the end of the circuit, we do readout. To readout, we adiabatically separate the two transmons. They were on resonance. We tune them away from resonance. The idea is that when they're on resonance, the eigenmodes are these logical 0 and 1. But as we tune one qubit away, these modes adiabatically transform into the pair states 1-0 and 0-1. And after we transform into that, according to that mapping, we just read out both transmons at the same time, and we get bit strings. And if the bit string was 1-0, it tells us that we were in the logical 0 state. And so our readout, in the end, gives us the following information. It says, are we in the logical 0? Are we in the logical 1? Or did we decay to 0-0? So that's one form of erasure detection at the very end of the sequence, so-called end-of-line erasure detection. It could also tell us if we were in the 1-1 state, for example, if maybe we had some process that took us there. So here's a really simple example of an experiment of this style. This is a Ramsey experiment on the dual rail qubit. So what we see here are fringes, Ramsey fringes between the logical 0 and logical 1 state. So these fringes evolve at a frequency that's determined by the frequency of the dual rail qubit. And we see that these fringes exist, but they kind of decay, and they decay according to this overall leakage into the 0-0 state, which is shown by this blue curve here. This is 1 minus the probability of ending in 0-0. So this sets an envelope for how much population you still have within the dual rail subspace. Okay, that's the core idea of how we operate the dual rail qubit. Another key idea is how we do erasure detection. And so I want to just introduce the mechanism here right now. We use a third transmon, an ancilla transmon, which is coupled to the dual rail pair. And the idea would be that while we're running a quantum circuit, while we're running some sequence on the dual rail qubit itself, we do erasure checks using this ancilla. And the erasure check should just raise a flag and say the dual rail qubit is in 0-0 at this moment in time, or not in 0-0. If it's not in 0-0, we don't want to learn any extra information about if it was in logical 0 or logical 1. So we just want 0-0 or not 0-0. To do this, we rely on a dispersive coupling between the ancilla and the dual rail qubit. So the ancilla will have some frequency if the dual rail qubit is in 0-0, and it will have another frequency if the dual rail qubit is in the logical 1 or logical 0 state. And you can see roughly where those frequencies line up. So the 0-0 peak is well separated from the logical 1 and logical 0 peak. So to do the erasure check, we do a pi pulse on the ancilla at this 0-0 frequency. This pi pulse is, in a sense, a conditional pi pulse that excites the ancilla only if the dual rail was in 0-0. Then we do readout. And in the end, our readout signal for the ancilla, we can apply some thresholding. And if it's in one part of the IQ plane, we say, okay, the dual rail qubit decayed to 0-0, and thus the ancilla got excited. Thus we read out this value. If the dual rail qubit is still in the logical subspace, then we get another flag that says not in 0-0. Okay, so this is the toolbox that is the kind of main ingredient for all the experiments I'll talk about. Microwave initialization, single qubit gates based on flux modulation, final readout, and then also this mid-circuit erasure detection. Okay, here's a little bit more about the device in particular. So it's a 3-transmon device. We have one readout line that couples to resonators for each transmon, so we can read them all out in parallel if we want to. We also have flux control and charge driving of all the transmons. As I said, the dual rail pair, we have one transmon that's mainly operating at its maximum frequency where it's most stable. And the pair that it's coupled to is tuned into resonance. The ancilla is about 1 gigahertz away for this dispersive coupling. And I want to just show a little bit of the coherence numbers for these transmons on their own. T1 times are a few tens of microseconds. T2 times are reasonably good if we're at the sweet spot, a bit lower if we're off the sweet spot. And if you look really closely, these numbers are a little bit worse than the microwave cavity numbers that we've seen at the millisecond scale. But nonetheless, we'll try to make a dual rail qubit out of this and see how it works. All right, quick water break. Okay. To characterize coherence within this excited manifold, is in some sense a process of post-selection. We want to run experiments where we do some coherence measurement on the dual rod qubit. And then we want to only look at instances where the system did not decay out of the subspace in order to evaluate really what was the coherence within that subspace in absence of erasure errors. So here's an example, much like what I showed before, where we do a spin echo experiment now. So pi half pulse, pi half pulse, characterizing phase coherence within the subspace. And again, we use this final readout to see how much contrast there is for the fringes between logical 0 and logical 1 up to this decaying envelope indicating that we leaked to the 0, 0 state. So the simplest type of post-selection would be to normalize these curves against this blue envelope. The blue envelope tells us that we decayed, so we don't want to include those shots. We only want to include shots where we remained within the subspace, at least according to this final readout value. So this is what that looks like when we post-select. This is just normalizing, again, these orange and green curves by this blue curve. And we see essentially coherence out to maybe 100, 150 microseconds. So this is quite a bit longer than the individual transmon T2, but this is actually limited by an entirely different mechanism. And so I want to tell you what this is limited by. At late times, let's say much longer than the erasure lifetime, most of the time the system has decayed to 0, 0. So we're post-selecting on a very small fraction of instances where the system did not decay. And it turns out this has a systematic issue, which is that we're using only the final post-selection, only the final readout to tell us if we stayed in the logical subspace or if we decayed to 0, 0. And this actually misses events where the system decayed to 0, 0 during the evolution and then heated back into the subspace. Those shots have lost all phase coherence, and they actually become a dominant contribution to how many shots there are where you end in the logical subspace if you look at really, really late times. And you can have a very simple model for this where you plug in essentially what is the decay rate, what is an estimate for the heating rate, and you see that it roughly is consistent with limiting how much coherence you can observe based only on this end-of-line erasure detection. So in order to do better than this, we need to do mid-circuit erasure checks. And this is actually representative of what you would do in an error-correcting code. In an error-correcting code, you don't leave your qubit for hundreds of microseconds and then check in the end. You actually want to do mid-circuit checks. So that's actually what we'll do in order just to characterize coherence within the subspace. This is the extra level of post-selection. So we have the final readout. We post-select on the final readout saying that we're still in the logical subspace at the end. And we additionally have a bunch of erasure checks that are applied during the circuit, which all are going to be included in our post-selection. So the post-selection is conditioned on all of the erasure checks saying that we never left the logical subspace. So we now have two things we can look at. First of all, we can say we do a spin echo experiment. As we increase the overall time, what is the probability of post-selection? So this probability decays exponentially because it reflects leakage out of the subspace. This is the so-called erasure lifetime, or the rate at which we leave the subspace and go to 0, 0. That's about 30 microseconds. This is really set by just the underlying transmon T1, the loss of amplitude. Conditioned on all of these checks returning that there was no error, this is now what our logical oscillations look like within the dual subspace. This is now at the level of like 500 to 600 microseconds. This is spin echo. If we do a bit more dynamical decoupling, we get up to the level of about millisecond coherence. So these could be compared to, for example, the underlying T2 times of these transmons. One of the transmons is at its sweet spot and doesn't really, and stays nearly T1 limited. The other transmon is off its sweet spot and has few microsecond coherence, which gets a bit better with more decoupling. But the dual rod qubit is more than an order of magnitude larger in terms of coherence within the subspace, post-selected against leakage out of the subspace. That's phase coherence. The T1 bit essentially characterizes, in the absence of leakage to 0, 0, what is the rate of bit flips within that subspace? And to measure this, we initialize the dual rod qubit in either of the two logical states, either logical 0 or logical 1. Again, we hold it for a long time now, and we do a bunch of erasure checks while we're holding it. And post-selected against no erasures, we see behavior like this. If we initialize in 1, it stays in 1 for quite a long time. If we initialize in 0, it stays in 0. And if we fit the differential between these two, this gives us essentially a rate of bit flips of about 0.9 milliseconds. So this is one round of characterization of the dual rod qubit post-selected against leakage. We have about half millisecond to a bit more than a millisecond phase coherence according to T2, a bit less than a millisecond for T1. And one way to define some notion of erasure noise bias would be to say, what is the ratio of these coherence times to the rate of leakage out of the subspace? The leakage out of the subspace is much shorter. It's only 30 microseconds. So this is one notion of erasure noise bias at the level of around 20 or a bit more.
Can I ask a quick question?
Yes, please.
What fraction of the trajectories make it to 300 seconds without?
Very, very small, roughly exponential of -300/30, which is at the level of 10 to the -4, something like that. So we have to do a lot of shots in order to collect enough statistics here. Okay, I haven't shown you the T2 star for the dual-row qubit. This is slightly a bit of a different story. So T2 star, this is characterized by Ramsey experiments. This measures the absolute frequency of a qubit over longer time scales. This characterizes over essentially as long as you're integrating, how stable is the frequency. We see some kind of funny behavior. So here's two example measurements. Each one we're integrating for about 1 minute. And in one measurement, we see kind of clean fringes. In the other measurement, we see some decay and revivals. So this is a little bit strange. It turns out, I'll just tell you, in a short story, the explanation here. It turns out that this beating effect comes from the fact that we see telegraph noise in the frequency of the dual-row qubit. And so if we integrate long enough over a longer time scale than the telegraph noise, it looks like decay and revivals in the frequency. This telegraph noise on the dual-row qubit is inherited from telegraph noise on one of the two qubits underneath. So this is now essentially rapidly alternating between a dual-row measurement and a measurement on just one qubit at the same operating point. They both have the same telegraph noise correlated in time. This in turn is inherited from some mode that we don't understand, which happens to be about 100 megahertz away from this operating point that seems to appear and vanish. So some kind of flickering mode, which we tentatively call a TLS. It couples to one of the two transmons, and it happens to also couple to the dual-row qubit in a remarkably similar scale. So it causes this telegraph noise of scale around 50 to 60 kilohertz on the transmon alone, and of the same scale on the dual-row qubit. A bit of a puzzle, I would say. And maybe you could frame it really positively as a tool for studying TLSs. And I think there actually is a lot of interesting physics in terms of understanding the TLS maybe should be understood as coupling individually to the different hybrid modes. And so you might want to understand how does the dual-row qubit ultimately inherit noise properties of the TLS itself. From a quantum computing perspective, this is a very slow process. This is tens of seconds switching time. And so a spin echo experiment does a very good job at resolving this, which is why it doesn't really show up in the spin echo measurements I showed previously.
Is the data in one of these two inverted?
I don't know for sure, but there's no real reason to believe that they should be shifting in the same way. It depends a lot on like what the relative frequencies are. I'm not even sure how if it's plus or minus, to be honest. Yeah. Okay. So I claim that the coherence within the subspace is better reflected by the dynamical decoupling data, not so much this slow telegraph noise. And one way to assess that is to try to say, how well can we do single qubit gates? So we do single qubit randomized benchmarking. We initialize the dual-row qubit in logical 1. We do a train of Clifford gates. Each Clifford, there are random Clifford gates. Each Clifford is composed of exactly 2 x90 rotations with appropriately chosen phases. We do this again in parallel with 11 erasure checks that are evenly spaced over the entire circuit. So just like with the coherence measurement, we can first look at what is the probability of post-selection as a function of the length of the circuit. This decays exponentially according to essentially an error per Clifford, which is just given by the probability that the system decayed to 0, 0 during each Clifford interval. Each Clifford, I should say, is about 100 nanoseconds. The X90 gate is 50 nanoseconds. Post-selected on all these checks, we see much longer timescale for erasures within the for errors within the subspace. These would be like the undetectable errors. So these are the bad errors. And indeed, it's a much lower rate than the rate of leakage out of the subspace. So maybe it's easier to think in errors for the X90 gate rather than Clifford. We have about 0.2% erasure per X90 and several, let's see, about 5 times 10 to the negative 5 for residual error that's undetected. So this amounts to a different notion of erasure noise bias. This is now the erasure noise bias during single qubit gates. So indeed, the dominant error on this qubit is leakage out of the subspace, which can be converted to erasures. Okay, I want to say one more point about coherence of the dual-row qubit, which is to say that the fact that the energy gap of the dual-row suppresses noise on the individual transmons can be a helpful tool beyond just its use as an erasure qubit. And specifically, you can imagine that you can operate this dual-row qubit anywhere that you can bring both transmons onto resonance with each other. With a normal transmon, you really would not like to operate off sweet spot very much because the coherence goes way down. But here we can suppress that noise and hopefully operate reasonably well off sweet spot. So here's an example of that where we do essentially all of those experiments, but now at a range of operating points spanning about 300 to 400 megahertz. And we see that over that range, one of the qubits which is already very far off sweet spot, stays pretty low, a couple microseconds. The qubit that's was originally on the sweet spot gets a little worse as we go off sweet spot as expected. The dual rail qubit stays at several hundred microseconds T2 time over this full range, except for one point where it seems to be coincident with another TLS, not the one that we looked at earlier. So this is a nice potential feature in terms of thinking about how robust these qubits can be in terms of can we find good operating points for them in a real circuit. We can think about, for example, tuning the operating point to dodge modes like this. If this mode happened to be at the sweet spot, we would be pretty unhappy, but we could actually tune away. It also could be understood as maybe relaxing some notion of the frequency targeting requirements, because you can just make everything a bit more tunable and just find some good operating point. So hopefully this could be a useful feature in terms of trying to make circuits with lots of dual qubits that are all working. All right. Let's go on to the last part, which is mid-circuit erasure detection. So we've already been using mid-circuit erasure detection for these coherence measurements. And I haven't said anything about how well they work. So let's talk about how well it works right now. To remind you one more time, we do these 0-0, not 0-0 erasure check by doing a conditional pi pulse on the ancilla followed by readout. That process takes about 880 nanoseconds. And that's set by the fact that we need to do a relatively long, slow pi pulse in order to resolve these two peaks, followed by a few hundred nanoseconds for readout. So how do you even think about how well erasure detection works? There's really three, in a way, independent metrics to try to understand this. One of them is your readout giving the correct answer. So that would be characterized by things like false positives. So if you were in the logical subspace and you do an erasure check, does it accidentally say that you had left the logical subspace? You can also have another readout error, which would be false negatives. So you actually did have an erasure, but your check failed to properly flag it. That would be false negative. A third type of error, which is independent from these two, is if I didn't have an erasure error, when I do my check, it should say not 0-0, but it shouldn't actually cause any additional dephasing on the dual rail qubit. If it does, that means you get a big penalty just for checking, and that's not allowed. That sacrifices any kind of noise bias that you hope to see. So these are all important things to characterize to understand how well this could work in an actual error correcting code. And they all actually impact the error correcting code in slightly different ways in terms of how they contribute errors of different types. So I wanted to spend one slide setting a stage for how to think about these numbers. So we're revisiting the idea of some kind of surface code enhanced by erasure checks that are for erasure errors that are flagged on these qubits. For any kind of syndrome measurement that we're doing, here's a really simple ZZ syndrome measurement. We'll think about maybe one concrete example for doing erasure checks, which is to just do lots of erasure checks at essentially the maximum rate, which would be like one erasure check for each qubit for each 2-qubit gate. That way you have high confidence that you didn't have an erasure between gates that you missed. So this would be essentially as many erasure checks as you might want to do. And in this case, you would think about errors induced by these erasure checks as adding on top of the errors of the 2-qubit gates. And so to understand what rate of errors can we tolerate for the erasure checks, we need to know what rate of errors can we tolerate for the 2-qubit gates themselves. So here's an example diagram from this AWS paper analyzing erasure errors. This shows essentially the threshold behavior for a combination of erasure and undetected Pauli errors. So if you have only erasure errors, you could tolerate up to about 5%. That's the threshold. Only Pauli errors tolerate up to about 0.7%. So just to set a rough idea of what we'd like to target, we'll just pick some point that's relatively deep below this threshold regime, where we say we'd like to have not much more than about 1% erasure per 2-qubit gate, and not much more than 0.1% Pauli error per 2-qubit gate. So again, we're not doing 2-qubit gates. We're trying to see if our erasure checks, how they stack up in terms of would they integrate reasonably well into this context. So these are our targets. Erasure errors should be less than about 1%. Pauli errors should be less than about 0.1%. So let's start with false positives. False positives are characterized by having the dual rail qubit in the logical subspace. So we initialize it in the logical subspace. We do an erasure check, and we try to confirm that the erasure check tells us that indeed no erasure had occurred. We do one extra thing, which is that we also read out the dual rail qubit afterwards, just to confirm that we initialize the correct state. And we see in this case around 0.5% or 0.6% false positive probability. This is limited by the fact that we have a little bit of unwanted excitation of the ancilla by accident. And this actually 0.6% is for one of the logical states. One should really average over all logical states, and that comes out to a bit higher at around 0.8%. So this is essentially false positive. When you get that, you have to treat it as if it was a real erasure error. So this essentially adds erasure errors to the system. And so this we want to compare to this target level. False negatives, we initialize the dual rel in 0, 0. We do an erasure check and we see if it correctly flags that an erasure occurred. And we see a little bit higher error here, now at about 1.5%. This is set by the fact that this error is flagged by exciting the ancilla, but then the ancilla has a small probability of decay during the readout. And so that gives a little bit of readout error. To think about how this enters into a surface code, if you were using it in that way, what you really care about is not just the false negative, but you care about the probability that an erasure occurred and then you missed it. So you have to combine these two probabilities. Both of them are low. The probability that an erasure occurred is essentially given by the erasure lifetime relative to the cycle that you're doing. And then you multiply that by the false negative. And we come out to about 0.04% chance that an erasure would have occurred in about the 1 microsecond time frame, and then we missed it in our erasure check. And these errors could be bad. They could introduce, certainly they persist as erasure errors, but they could propagate to Pauli errors. If you had an erasure and you missed it, then you do 2-qubit gate between that qubit and another one, that could actually induce Pauli errors. So these we should compare to the 0.1% threshold. Okay, last one would be when we do erasure checks, does it induce extra dephasing on the dual rel qubit? And here's how we characterize that. So this is a spin echo experiment where we do a fixed evolution coherence measurement. So we characterize how much coherence is left on the dual rel qubit after a fixed time of 114 microseconds in particular. We characterize this by actually applying this final pi/2 pulse along different phases, and we can essentially measure the length of the block vector along the equator. So it's really like the length of the x and y components of the block vector. So we do that as a function of inserting more and more erasure checks during this gap. And here's roughly what we see. So the degree of coherence is the length of the block vector along the equator. When we go from 0 erasure checks to a small number, it almost looks like the coherence gets better. This is the phenomenon that's tied to this idea that if we didn't do any erasure checks during the circuit, then we start to include events where the system decayed to 0, 0 and then heated back into the subspace. So that appears to lower the amount of coherence. If we start doing more erasure checks during this evolution time, then we throw out those instances and we're left just with the instances where the system stayed in the subspace. So that accounts for this initial apparent rise. Once you do sufficiently many erasure checks, this effect should plateau, and you should be left with just how much coherence is left after 100 microseconds in the absence of erasure errors. That's about 80%. That's roughly consistent with like a 500 to 600 microsecond T2 time. So that reaches a plateau, and then you say, how much loss of coherence do I get for each extra erasure check that I do? This is a pretty conservative upper bound. The slope here is actually at about 0.03%, but this is a conservative upper bound because it's hard to completely rule out that we haven't, maybe this effect would continue growing over time and then it counteracts some decay. So this is a pretty conservative upper bound of about 0.1% dephasing error per erasure check. So to recap, we have about 0.8% probability of injecting an erasure error every time we measure. We have some less than 0.1% chance of missing an actual erasure event that happened, and less than 0.1% chance for inducing extra dephasing. So these numbers are reasonably compatible with this type of error correction target that we're looking for. This is not the full story, of course. There's more things that would be needed in a real surface code. We would need to, for example, do erasure checks, reset the ancilla, probably reset the dual rel qubit as well if an erasure was flagged. And this erasure check also takes about a microsecond. Ideally, it would be as fast as the fastest thing that we're doing in our circuit. And so we anticipate that 2-qubit gates, for example, could be done in just a couple hundred nanoseconds. So in that case, we would want to do faster erasure checks as well. All right, so that brings me actually to pretty much the end of the talk. I'll just briefly highlight again, millisecond scale coherence within the dual rel subspace, post-selected against erasure errors. That translates to a erasure noise bias of several tens up to like maybe 20 to 40, both for idling errors and for single qubit gates. We can also operate the dual rel qubit over a reasonably broad tunable range, which is relatively unusual for superconducting circuits, which typically have to operate near a sweet spot. And finally, we can do erasure checks without introducing very many errors into the dual rel subspace. So hopefully this is a compelling picture to you that this could be actually a surprisingly coherent building block for quantum error correction, given that the transmons underneath are relatively noisy. And I want to just say a few words about what some of the most critical next steps would be. So first of all, as I said, when we do erasure checks, we need to respond accordingly to the flag that we get. So that would be resetting probably the ancilla and also resetting the dual row qubit. Better forms of erasure detection are possible. This method that we used where we have an ancilla-qubit, it's actually relatively costly. It's a whole extra transmon that's being used just to do erasure checks. It's also kind of slow because you need to do a conditional pi pulse followed by readout. There are other schemes that are much more compact. So here's one example where you have one readout resonator coupled to both transmons from the dual row qubit. And this readout resonator can by itself be used to directly probe erasure errors. And so that could be a much faster and more compact method. And then, of course, 2-qubit gates. One would need to really be sure that the 2-qubit gates still benefits from this noise suppression. So if you somehow lose your noise suppression, if you break the resonance between transmons during 2-qubit gates, then your 2-qubit gates will not have the same erasure noise bias. They'll have extra dephasing error. So one needs to make sure that the gate scheme is compatible with preserving this noise suppression. So I think it's a pretty exciting path towards hardware efficient error correction using some of the really familiar transmon-based building blocks. So I want to just acknowledge the team at AWS that worked on this project and the entire AWS Center for Quantum Computing, which all contributed in various ways to this. And finally, thank you very much for your attention.
Okay, yeah, we have lots of time for questions.
I can hear you, but probably not.
I will speak loud. How do you ensure chi matching of each of the transmon to the third one? Do you use like tuning of the third transmon?
Chi matching. So are you?
I'm referring to the fact that the frequency shift of the third transmon condition on 0, 1 matches very well the one of 1, 0.
Yeah. Let me just
in the erasure check. Yeah.
So it's the fact that these are lined up with each other?
Yeah.
Yeah. So a couple answers to this. So first of all, the simplest answer would be these are pretty well matched to each other because the logical 0 and logical 1 are composed of even combinations of left transmon excited and right transmon excited. Only one of the transmons is actually coupled to the ancilla. At least one is coupled much more strongly to the ancilla. So if you had just the bare 0, 1 and 1, 0 states, then only one of those would get a dispersive shift. But because these states are equally supported on both transmons being excited, it roughly balances out. So that would be the first answer. Even without thinking too much, and you just couple the ancilla to one of the transmons, you already get structure like this. The small gap here between these two peaks, that is set by some details like how detuned are you from the ancilla, and you could actually tweak this by adding a little bit extra coupling or adding a little extra coupling from the other transmon to the ancilla. So that would be one answer to that question. A second answer is that you don't need these to be perfectly matched, actually. So the scheme that I'm describing here is a conditional pi pulse that should only ever excite the ancilla if the dual row qubit is in 0, 0. So let's say that these were not very well matched. If you did a sufficiently narrow pulse on the 0, 0 transition, you would actually be very insensitive to this level of matching. Maybe you would care if you have thermal fluctuations in the ancilla or other uncontrolled population in the ancilla. But at least within this kind of simple model, it's actually not that sensitive to it.
So towards the end, when you were showing the effect of your erasure check on the qubit subspace itself, you call the degree of coherence or something. What was included in calculating that number? Like, is there any additional leakage introduced by your erasure check? Was that number included in that? And you only said the word dephasing per check, but what about bit flips? So like basically, like what is the different types of errors that could have happened, and did you characterize all of them?
No, we did not characterize all of them. This is really just as shown, which is we measure the length of the block vector along the equator of the blocks here, and we say how much does that get worse as we do more erasure checks. So this isn't exactly a measure of bit flips, but if you had a lot of bit flips, then that probably would be reflected to some degree in this. Is that not the case?
It's a different axis of block sphere.
Okay, I think that's right. So then this does not capture that. I think we could probably bound that probability in different ways. We could certainly bound that probability using the T1 measurement, where we just initialize one state, we do a bunch of erasure checks, and we see that it doesn't stimulate very many transitions between the two logical states. So maybe we'd need a different way to characterize that.
Also, another comment, you had a point where you said that missed erasures, you counted that in poly errors. I would be a little bit careful in doing that because missed erasures spread farther in your code than just simple poly errors do. And so they're going to have a worse effect than just local poly errors.
Okay. Okay, maybe we could talk after. I'd like to understand that a bit better.
So two quick questions. One, the TLS thing, it looked like the hybrid mode and the Q1 mode both moved by the same amount.
Yeah.
But you said it should be quadratic.
Yeah, quite right. So here's my best explanation. So that was my same thinking when I first saw this. I thought the dual qubit is fluctuating by 60 kilohertz. Surely that must be explained by much larger levels of fluctuation on the underlying transmons. So the reason why that doesn't quite hold is because that logic is to say you have your TLS that's coupled to your transmon. You have to first analyze that by calculating the dispersive shift, like treating that now as like a longitudinal coupling between the two, where all it does is a frequency shift on the underlying transmon. That turns out to not be an accurate approach. What needs to be done first is to diagonalize the dual qubit and say we have these two hybrid modes. These two modes are now differently detuned from the TLS. So the TLS is coupled to one transmon, so that means it's coupled to both hybrid modes. But if it's nearly resonant with one of the hybrid modes, then it dispersively shifts that mode by an amount that's of the same scale as how much it can shift just one transmon underneath.
So you're protected against like flux drifts, but not nearby qubits, basically.
You're not protected against nearby coupled elements. Exactly. Yeah.
Okay. And then the second quick question, as you pointed out, you have readout resonators on these things.
Yeah.
And the chi's of these two hybrid modes are basically the same.
That's right.
Why not just read out the resonator? Why do you have to faff around with the ancilla?
Yeah. So the chi is the same, but when you put photons in the readout resonator, it now actually changes the energy gap of the dual. So for example, let's say you probe a readout resonator, which is coupled to just one of the two transmons. Then if you put several photons in that resonator, it breaks the degeneracy because it shifts one of them by chi. So you're right that the effective chi is the same, but there's extra terms in that Hamiltonian that leads to dephasing when you start putting photons in the readout resonator. Thank you.
You've said that the fidelity of the single qubit gate is more accurately reflected by the T2 rather than T2 star. Can you explain why that is?
Yeah, I guess I would say that when you do randomized benchmarking, you're averaging over all axes on the Bloch sphere. And so it's more akin to a dynamical decoupling experiment than to a T2 star experiment. That would be my rough argument. Are there objections to that? Or we can discuss?
I had two questions. One was, what's the temperature of the qubits? And then the other one was, what do you think the residual noise, where it's coming from? Is it flux noise? Is it other TLS garbage? Who knows?
Yeah. Okay, so temperature of the qubits comes out, I would say it's hard to characterize super precisely. We measure about 0.2% thermal population in the transmons, which comes out, I think, to about 40 millikelvin, 35 millikelvin, something around there. That is an important parameter if you do this measurement where you don't do mid-circuit erasure checks, because that determines how much of this decay heating process there can be. But it's not as relevant if you're doing mid-circuit erasure checks. So that would be to the first question. Residual noise. So there's many potential noise sources, and I would say that we don't have a full understanding of what limits the current level of performance. A couple of things that we think are likely limiting. So we think that there is some residual flux noise, not at low frequency, which would look like dephasing on the single qubits, but a little bit of noise at high frequency, which is actually at this 2G energy gap at about 180 megahertz. This probably is from like thermal noise on our flux lines. That would roughly come out to predicting about a millisecond timescale for bit flips within the subspace. So we think that that's probably one dominant contribution. Noise on the individual transmons is actually quite well suppressed. So we think that that should not be explaining the 500 microsecond T2 time. So we don't quite know what explains the drop to this T2. A couple possible explanations. We do have this TLS, it fluctuates. We decouple at least from these really low frequency jitter in this presence of this TLS. But it does mean that we're hybridized by a small amount with the TLS. If the TLS has its own dephasing time, it's possible that that could add to the dephasing that we see. And yeah, so those are a couple of the main sources that we thought
And
about.
you also showed the TLS, did it come and go?
Yeah.
Sometimes you get telegraphs. So do you get the best data when the TLS is gone? Or when the TLS is there, did you try the same thing to see how it hurts the performance?
It comes and goes on second timescales, and because we need to do many shots for all these experiments, like hundreds of thousands of shots, because so many of them are thrown out in the post-selection process. So that means we're really integrating for like long timescale, hours. Some of these measurements are integrated or interleaved over like day-long timescales. So we don't really do that. No, I mean, that might be a nice thing to check, would be if we look at data just when the TLS wasn't there, is the coherence any better? I don't know the answer. Yeah, thanks.
Okay, I think in the interest of time, we'll move on to the next speaker. Let's give another round of applause to Harry.